Hello and welcome to Lesson 3 Acceleration. In this video we're going to be looking at example 1 in the workbook, and it is actually the only example for this lesson. This example is going to be dealing with a value of negative acceleration actually. So if we want to talk about acceleration really briefly, the typical acceleration we think of is when we press on the gas pedal in a car. The sensation of a positive acceleration is when we are increasing our rate of speed. For increasing our rate of speed, we have the feeling of being pushed back into our seat, right? A negative acceleration is often referred to as deceleration. And when you decelerate a vehicle, you slow down. It's pushing on the brakes. You get the opposite feeling. You get the sensation of being pushed forward into your seatbelt. That's a deceleration or a negative acceleration. All right, let's jump into our first example problem here, and we will see where this takes us. The example states, while braking, a car experiences a backward acceleration. See, already it says that we're braking, we're slowing down, we're backward accelerating. Okay, the backwards acceleration is measured at 7.40 meters per second for a time of 2.88 seconds. All right, looks like we already have a little bit of relevant information here. So let's say we want to put down our acceleration. I have a strange color on right now. Is equal to, make sure you don't forget to put the negative symbol, because this is a negative acceleration. It's slowing us down. Negative 7.40 meters per second squared. The units for acceleration, meters per second squared. And we're going to play around with these units a little bit later on. Okay, we also have this time given to us. Time given to us is 2.88 seconds. Great. What else does this question say? The question says, at the end, it is moving forward at 31.5 kilometers per hour. What is the initial velocity? Interesting. Okay. Well, I want to lay out what's going on here if you haven't picked it up already. I changed my color. What it's saying is that we have a car that's moving quite quickly down the highway with some initial velocity, and it pushes on the brakes. That gives it a fairly reasonable deceleration for 2.88 seconds. So it's moving quickly, pushes on the brakes, but it doesn't stop. It just slows down for a couple seconds. So maybe it saw in the distance there was a police officer with a radar gun and they were speeding. So they quickly slammed on the brakes so they wouldn't get a speeding ticket. Okay, so let's do a little diagram. We have our car. This is just going to be a box, but it's a car. And it is moving at some initial velocity. I'm going to put VI, the I for initial. I'll hat on there. And it is, well, it's some velocity. That's what we're solving for, right? And then, in the middle here, there's some deceleration value. And it tells us, this is our car still, our final velocity, I'm going to make this line smaller because it's a smaller value, is going to be VF, F for final. It's equal to 31.5 kilometers per hour. All right. Great. I'm going to also record that down here. So our VF is equal to 31.5 kilometers per hour. Thing I noticed right away, this is not in SI units. This is kilometers per hour. We're going to be dealing with meters per second squared in seconds, which is going to lead us to meters per second. So we're going to want to convert that right away. But anyways, in our diagram, what is slowing this down? Well, what's slowing that down is it's the brakes of the car. All right, the driver obviously decided that they were going too fast and they needed to slow down. So this is they're braking, which we haven't learned forces yet. We will soon. But this is going to cause some sort of force. The brakes are causing a force to slow down the car. Perfect. Now, the steps to actually solving this problem, now that we know what's going on. How are we going to determine this change in speed? Because at some point here, we're going to have a change in velocity. Well, we know the rate of the acceleration and we know the time given. And if we utilize the formula given to us at the beginning of the lesson, we can say that, well, A, acceleration, is equal to the change in velocity. I didn't put my little hat on up there. Over time. Well, we're already given acceleration and time, and we're looking for velocity. So this is sort of a straightforward solve so far. Let's rearrange our formula. We're going to multiply both sides by t to get rid of our denominator value there, and also to get delta V all by itself in one step. Then we're going to have the change in velocity is equal to TA. All we have to do now to solve for delta V is stick in our values. So delta V is equal to 2.88 seconds times negative, keep our sign on there, 7.40 meters per second squared. I'm going to do a little bit of unit analysis on these units as well really quickly. We have this second, which we're multiplying in our numerator, and this second squared is in our denominator. Really, what second squared is saying is it's saying that there's 2 seconds down here, right? Seconds times seconds. Well, this second is going to cross out one of these, which effectively cross out that squared symbol. It's going to leave us with the units meters per second. If you're not comfortable with this yet, don't worry. Again, this comes with practice, and it's something that you're eventually going to work into. But keep this in the back of your head, that units, just like our numbers, are going to be working out. All right. So, what do we have next? Delta V, change in velocity, works out to, I worked it out here somewhere, negative 21.312. Negative 21.312 meters per second. That's our change in velocity. So, the car was initially going 21.312 meters per second faster than 31.5 kilometers per hour. Well, what does that mean to us right now? Not too much yet, because we don't have this in meters per second. So we have a disconnect of units here. We have to convert that. So let's do our conversion. By the way, this was, we'll call this step 1. And over here, I'm going to do step 2. Maybe I'll do it up here. Step 2. Okay, we're going to convert VF. Okay, and here what did we do? Here we solved, no, just solve. We didn't solve delta V, the change in velocity. Okay, so when we're converting our final velocity, what do we got to do? Well, we start with 31.5 kilometers per hour. And what did we do in the last lesson? Well, what we did in the last lesson is we did unit analysis. And we know that in 1 kilometer, we have 1,000 meters. So what we can do is what we're going to do, multiply by 1,000 meters per kilometer. I'm going to put 1 kilometer here. This is effectively multiplying by a value of 1, which isn't going to change anything but our units, right? Our kilometer value can get crossed out. We run this math, and this works out to, well, we move the decimal 3 places when we multiply by 1,000. So 31,500 meters per hour. We're halfway there. We're now in meters per hour rather than kilometers per hour, but we want meters per second. So the second step is converting meters per hour to meters per second. In the previous lesson, I showed you how to convert 1 hour to seconds, and it works out to 3,600 seconds per hour. And that's because there's 60 seconds in a minute and 60 minutes in an hour, so 3,600. All right, we want seconds on the bottom, and we're going to be canceling this h. So we're going to say 1 hour over 3,600 seconds. Hours cancel. We divide 31,500 by 3,600. And this is going to give us a value. So VF in meters per second works out to, I also have this here somewhere, 8.75 meters per second. All right, we are almost done this problem. We now have our change in velocity. We have our final velocity. What we know is that, well, all we really have to do is add this value on here, and we've got what we need. All right? So we can say what's the change in velocity formula? Our change in velocity is equal to our velocity final minus velocity initial. Will that do it for us? That should do it for us. All right, if we want to rearrange this to find VI, we're going to say, well, we're just going to add VI. No, hold on. We got to do a double flop here. So it's going to be kind of two steps. We're going to say that, yeah, we got to do two steps, unfortunately. We're going to add VI to both sides. And so we're going to have VF is equal to VI plus delta V. And then to get VI all by itself, we're going to say that VI, so what we're doing is we're subtracting delta V. And up here, we're going to subtract delta V. So we're going to have VI is equal to VF minus delta V. All right, I missed a whole bunch of hats up here, but I hope that gets the point across. Now, the reason we had to do that is because either we could leave a negative VI and multiply by -1, or we could just do a two-step rearrangement. Again, as you get more proficient at this, you can largely do these rearrangements in your head even. But I want to kind of show off how at the rudimentary level we're actually accomplishing this. If you're confused by this, come talk to me. I'll get you some practice. We'll get you through this. The algebra shouldn't be what's holding you back right now. Okay, so let's add our numbers in here now. VI, what we're finally looking for, is equal to VF, 8.75 meters per second. Minus negative, right? Because this is minus symbol here, but we have a negative delta V here. So minus negative 21.312 meters per second. Well, a negative of a minus essentially turns this into a plus symbol. Okay, so we're going to be adding these values together. So VI is equal to I get 30.1 meters per second. And I rounded off my sig figs here. So 30.1 meters per second. And that is the final answer. I didn't put my meters per second here. Turn that tool off. Meters per second, right? 30.1, we have 3 sig figs, so that's our sig fig check. 3 sig figs, 1, 2, 3, 1, 2, 3. That's it. I hope that helps. And if you have any trouble on any of this algebra, please come talk to me and get some help, because I really don't want that to be your limiting step.